Okay, let's do a little bit of review. Let's talk about standard deviation, and let's talk about an expectation and a deviation about that expectation, and we'll just review some of the statistics here. So remember the formula, it's the square root of the average of the squared deviation from the mean. And so I have a set of data, I have an average for that set of data, and what I want to know is how far is each point from this average. And I can't just take the difference and add them up because positive numbers and negative numbers would cancel each other out, and so I square them. And so I take the squared deviations from the mean, I average those, and then I take the square root. And so this ends up giving me the same units, which is really nice. So let's assume that I have the average height of all the students in a class. And the average height of all the students in a class, I have 30 students in the class. I get everybody's height. Do I measure, or do I ask you how tall you are? Okay, so I measure how tall you are, and from that I compute, I have 30 different data points, and from this I then compute an average, and then I take every single person's height relative to this average. And if you're taller, this is a positive number, and if you're shorter, this is a negative number, and I get all these deviations. But if I take these deviations and just add them up, they're going to cancel out, and so I square them. Now, the units are going to be inches, which is the height of each person, and the average, which is also inches, so inches minus inches is still inches. I square it, and I get inches squared. Well, sum them up, I still have inches squared. Divide by the number of observations, I still have inches squared. That doesn't really help me, so that's why at the very end I take the square root. And so the units of the standard deviation are the same as the data. Okay, two ways to compute expectation and standard deviation. The first is using historic data. And I take all past observations and I assign them effectively the same weight, which is 1 over the number of observations, or 1 over n. And essentially this is an unbiased estimate. I don't have any reason to believe that the earlier observations are more likely to happen than the later observations. I don't have any reason to believe that the conditions in one year that caused a specific observation is more likely to happen or less likely to happen than the conditions that cause a different observation. And so if all past observations are equally likely, I have an unbiased sort of estimate. I just add up the observations and divide by the number of observations to get my mean, sum divided by n, and my standard deviation is going to be each observation minus the average squared divided by, and the reason I divide by n minus 1 is that I have a sample and not the population. I don't know every single observation. I just have some sort of sample. Even if a company's only been around for 5 years and I have all 5 years worth of data, since I'm trying to forecast forward, I'm taking a sample of the different conditions that might cause observations, and so it's still a sample. Dividing by n minus 1 as opposed to dividing by n gives me a larger variance and therefore a larger standard deviation, and the confidence interval and the likelihood that I can compute from this statistic would be even larger because I don't know every single possible outcome. So that's the first way to compute it, is using historic data. Just sum them up, divide by the number of observations, sum up the squared deviations, divide by the number of observations minus 1, and then take the square root. The second way to calculate an expectation or a deviation about that expectation is if I have states of natures and probabilities. And I might decide, well, let's just sort of go through the notation first, and then we'll talk about why you would do this. So I might have different outcomes, and the outcomes, we use the statistical language, we call these states of nature. And it might be that I have a boom and a normal and a bust, or I might have war or no war, or I might have famine or no famine, a number of different possible states of nature. And so for each state of nature, I have a probability of a state of nature, and these of course must sum to 1, and then I have a return given that state. And so now to compute the expected return, I take the return given the state times the probability of the state, and then I sum across all the different possible states of nature. And similarly, I calculate a standard deviation using each returns given the state minus the expected return times the probability of that happening. I square that, I sum those up, I take that to the 1/2 to get the standard deviation. We will do this with some data to sort of see what the differences are and to see what the different outcomes are. But essentially, I have two different ways to compute the expected return, and I have two ways to calculate a deviation about that expectation. The difference is here, any bit of past data I assume is equally likely. I have no bias. I give them equal weighting. Here, I'm deciding, I think there are actually different probabilities of different outcomes. I want to assign different probabilities to different outcomes, and I can do this as well.